modeling and coastal inundation. So in IIRS, my research interests are numerical modeling of tsunami, storm surges, and machine learning. So in this 45 minutes to 1 hour of lecture, we will discuss about how we model tsunami and how in real time we model tsunami here in Indian Tsunami Early Warning Center in IIRS. And then I give a time of 15 to 20 minutes. You can go ahead with your questions. Let's start. So in this lecture, I have divided the present discussion or presentation, whatever let's call it, into a general introduction. I'll say like why numerical modeling is important with a few basic examples. And then I discuss about various types of numerical models and why numerical modeling is important. And then we discuss about the basics of tsunami and how tsunami is modeled. And then we'll go for your question sessions or a discussion. So next, let's start with a basic introduction. I'll take a problem of sloshing. It's a highly important and basic problem in mechanical engineering. See, this is a tank, a transparent tank of certain finite length and finite width, filled with water, and this tank is excited horizontally here. Tank is excited horizontally. So when tank is excited horizontally, there will be a disturbance on the free surface. It is called as free surface of the fluid. Because of these horizontal excitations, the free surface will oscillate. The free surface will take certain height perpendicular to the free surface. So the phenomenon of disturbance on the free surface due to external excitations, we call it as sloshing. So sloshing has a lot of or immense importance in real life. So let's see yet another example. Even this is an example of sloshing, but here compared to the previous slide, here the tank is of a bit higher dimensions. So we have width of the tank, we have length of the tank, and depth of the tank. Here the length of the tank is around 2 meters, and it is filled with the water of depth or height 1 meter, exactly half of the length. Now it is that the tank is placed on the shake table. It is excited vertically. There is a disturbance on the tank. See, the base of the tank is excited vertically. So when there is external excitation, there will be a disturbance on the free surface, and the free surface will oscillate. Now here you can see a very small height. When this tank is vertically excited, the disturbance is very small, very minute. Now this plot shows the time versus height plot. You can see that the height is in centimeters. Hardly there is a amplitude of plus or minus 1 centimeter. There is no much disturbance. Whereas in this example, if you see, the same tank is excited vertically, but with a different frequency and with a different acceleration. Now you can see the disturbance on the free surface. There is a huge difference between this case and this case. The free surface is oscillating and the height is continuously increasing. The height is so increased that at some point the water has sloshed out. Now this is the plot of height versus time. If you see, as the time increases, as the excitation goes on, the height of the free surface was exponentially increasing. You can see the height was exponentially increasing. At one point, the water sloshed out. Now the point I would like to raise here is, here both the tanks are excited vertically. In this case, the free surface was unstable. I mean, the water has sloshed out. There was exponential increase in the wave height. Whereas in this case, the water is stationary. I mean, there is no exponential increase. There is a bounded oscillation. Why the difference? So we call this as stable. We say the free surface is stable here, and we say the free surface is unstable here. Now the difference is, in this case, the external excitation was sufficient enough to provide energy to the free surface, so that the free surface was continuously taking the energy and it was keeping on increasing in its height, and it is sloshed out. Whereas in this case, the external excitation is not sufficient enough to excite the free surface so that it can undergo this instability. Now, this is a typical stability chart I can plot, taking the acceleration of this tank on the x-axis and uh, taking the frequency of the external excitation on the y-axis. I'll keep on increasing the acceleration of the external excitation. I keep on changing the frequency. I see whether the free surface is stable or not. If free surface is unstable, I'll plot with a dark color. So I end up with such a chart. So in this chart, if my acceleration of the base excitation and frequency are within the plot, I'll experience this kind of unstable behavior. If the acceleration and frequency of the base excitation are in the white region outside, I will experience this kind of behavior. Now, the point is why I have given this example is imagine this tank to be of infinite length. Say the width or length is really infinite and the width is infinite. And imagine in that case, the free surface is going to be infinite, a huge area. And imagine depth to be of a few kilometers, 5 kilometers, 8 kilometers like that. So in that case, we can extend this to a ocean. Here in this example, the external excitation was the base excitation. In real life, there would be, in real life, if this length of it are infinite, if it is an ocean, there are multiple external forces acting on it, on the free surface. On the free surface, we have gravitation of sun, moon working on it, the rotation of the earth, the Coriolis force working on it, the external wind working on it, the circulation, and lot of complex phenomenon will undergo in the depth, and multiple forces will act on it. Now imagine we have a seabed at the bottom. We have a seabed at the bottom, and there is a disturbance. Imagine this to be an earthquake. See, the shake table is giving energy. So if it were a seabed, if it were an ocean, we have complex tectonic plates under the seabed. If they are diverging continental plates, then they move. There will be an earthquake. Either they move horizontally or they move vertically. When they move it, they impart sufficient energy to the free surface. The free surface will be disturbed, and there is a cause of tsunami. So we can extend this example to the case of tsunami. That's why I have shown you this example. Next, to solve this sloshing problem. Now, this sloshing problem occurs in different places. Now, I want to study the problem of sloshing. I want to find out in what frequencies, under what excitations, my free surface is unstable, and at what height the free surface is rising. What is the height of the free surface? At what cases, at what external excitations and frequency, my free surface is stable. I'm interested in knowing that. To know that, we know that every phenomenon is governed by certain physical laws. When we apply these physical laws, we end up with the conservation laws, like conservation of energy, conservation of momentum, conservation of mass, etc. When we apply these conservation laws along with the fundamental laws of physics, we end up with ordinary or partial differential equations. We'll end up with ODE or PDE, ordinary differential equations, and or PDE, partial differential equations. Now, if we solve these partial differential equations, then I can find out to what height the free surface will rise, to what external excitations my free surface is stable, right? So to summarize, every physical phenomenon is governed by laws of physics. When we apply these laws of physics, they lead to conservation laws. These conservation laws end up with certain mathematical ordinary differential equations or partial differential equations. And we have to solve those ordinary or partial differential equations to study the phenomenon. So here in this sloshing problem, the complete domain, the tank, can be excited horizontally with external excitation xt, can be excited vertically with external excitation yt. The complete domain, the fluid, obeys this equation, del square phi equal to 0, a Laplace equation or a Fourier's equation. Phi, the unknown, is called as potential, velocity potential. Now, with these governing equations, my aim is to solve the velocity potential phi. If I know the velocity potential phi, I can calculate the velocity of the free surface of the fluid. If I know the velocity, I can calculate the height eta for the given external excitation xt and yt. Okay, so in this, my aim in this sloshing phenomenon, my aim is to solve the wave height eta for the given external excitation xt and yt. If I know eta, after solving, I can have such plots, time versus amplitude. I can find out whether my system is stable or not. Now, to solve this, we have a governing equation. We have a set of boundary conditions. Now, the complete question boils down to how we are going to solve this unknown velocity potential phi. So, to solve it, we have three methodologies. First is the analytical solution. Analytical solution in the sense, we have these equations. For this, straight away, we can get a closed form solution. Like, for example, if we speak of a simple pendulum, right? I have a simple pendulum above like this. We know its equation. Its equation is d square x by dt square plus omega square x equal to 0. It has got a closed form solution. My solution will be x is equal to, sorry, I'm writing with mouse, it's quite tough. So x is equal to amplitude a naught into sine term into omega t plus phi, right? Omega t plus phi. So this is going to be my closed form of solution. So analytical solutions are possible. Analytical solutions are possible whenever we have simple differential equations. But here in this differential equation, it is pretty complex. In every case, the analytical solution is not possible. Only for simple cases, analytical solution is possible. Say, for example, simple pendulum, its differential equation is d square x by dt square plus omega naught square x equal to 0. Second order homogeneous differential equation. It is quite easy. We can take a simple paper and pen, apply some trigonometry and simple harmonic analysis to it, and we can end up with a closed form or a formula for the solution. But in real life, we end up with complex problems. So it's not easy to have analytical solution for every phenomenon, every problem. Likewise, for this Gaussian, it is not possible to have the analytical solution. So this solution is ruled out for complex problems. Next problem is, next thing to solve is experimental analysis. Here you can see this is a typical experiment which we have conducted. But experimental analysis is not possible for every case. Here in this case, the tank was rectangular. How about if my tank was cylindrical? How about if my tank was spherical? How about if a tank was annular? How about if my tank was a toroidal, etc. So depending on the shape of the tank, I cannot conduct every experiment because conducting experiment is a very costly process. Also imagine inside this, instead of water, there is some flammable or some acid kind of liquid. In that case, it is really complex to do experiment. It might lead to hazards or accidents. So experiment is a costly process and the experiment cannot be done for every case, right? So experiment is a costly process and experiment cannot be done for. Okay. We have different steps involved in the numerical methods. So real world problems, we apply numerical methods to it. So various methods are available. So whenever we speak of numerical methods, we have 3 steps involved: pre-processing, mathematical solution, and post-processing. Pre-processing involves defining the geometric properties, defining the material properties, defining the mesh, defining the length, dimension, etc. Having a good mesh. Mathematical solution depends on what numerical method you're going to apply, finite difference, finite elements, what kind of matching schemes you are going to apply, the mathematical part of it, and post-processing. After seeking the solution, how you are going to visualize. After seeking the solution, time step. After seeking the solution, how you are going to visualize. After seeking the, what is my wave height at a given location at a given time? What is my wave height, etc. Plotting tools and all comes under post processing. So whenever we speak about numerical methods, we need to code these numerical methods into a programming language. So various programming languages and commercial open source packages are available. The popular programming languages are C, C++, Fortran, Python, R, Julia, MATLAB, Octave, Scilab, etc. With these packages, these programs are some high-level programming languages and fewer low-level programming languages. Whenever you try to implement your numerical method, you need to code right from the scratch. You need to take care of pre-processing. You need to take care of mathematical part of it. You need to take care of post-processing. You need to code entirely from the basic. Also in the market, commercial softwares as well as open source packages are available. These packages are like GUIs, graphical user interfaces, where you have predefined functions, predefined tools. You need to just find out which tool is applicable to what problem. Just plug in the tools and get your problem solved. Get your ordinary differential equations or partial differential equation solved. So the commercial packages to open source packages quite famous in the market are Abacus, ANSYS, Custom, Fluent, and OpenFOAM. So all these packages, they work on different numerical methods like finite difference method or finite element, finite volume, etc. Now, this is about the introduction of numerical methods. Let's come to the basic topic, tsunami. Now, how tsunamis occur? So say this is ocean. This is the free surface of the ocean, deep part of the ocean. Under the ocean, this is a seabed. So we have tectonic plates. These are converging tectonic plates, one plate above the other. So these plates always try to move. So they are in the motion, and they have a tremendous pressure build in between the contact area. This one plate will try to climb or come over the other. So when they do that, earthquake, they release a sudden energy. There will be a sudden slip. Enormous amount of energy is released. That is called as earthquake. So that earthquake will be distributed. That earthquake will be released in all the, that energy will be released in all the directions, 360 degrees. And exactly at the top surface, that energy will be given to the free surface. So this energy will be taken by the free surface, and free surface height will rise. And under the gravity, as this rose to some height, there will be a gravitational pull because of its mass. It will try to fall down. Under that phenomenon, it will move towards the coast. It will move towards the coast in all the directions. So this phenomenon where earthquake is created, we call it as generation. So energy releasing and free surface deforming, or free surface going to certain height, we call it as generation. And under gravity, the free surface will propagate towards the coast. We call it as propagation. So let's continue with the video. A problem in playing the video. Let's see. Yes. So the rocks or the continental plates are under huge tremendous pressure. So suddenly there is a motion and the energy is released. The free surface has deformed. So this is the deformation in all the directions. And this free surface will propagate towards the coast. And when it crosses the coast, it will enter into the land and it will inundate the land. So the complete tsunami process involves three different steps: generation, propagation, run-up, or inundation. So for generation, there is an earthquake. Energy is distributed in all the directions. Exactly above where there is earthquake, exactly above the disturbance is propagated to the free surface. The free surface will rise to certain height, leading to deformation. Under gravity, it will propagate. So we call it as propagation. So we call it as propagation. Here it propagates. It enters into the land, and inundation, it's called as inundation. So there is tsunami. The disturbance on the free surface might be because of different phenomena. Tsunamis are generated by different phenomena like earthquakes. They can be even caused by landslides. Next to the seawater, there is or under the seawater, there is a huge land block which has moved. This will displace the free surface. It will generate. It will propagate. It will create disturbance on the free surface. It will generate deformation, leading to propagation and inundation. Or some under the seabed, there might be a volcanic eruption. This volcanic eruption will create disturbance, leading to deformation. Under gravity, the deformed wave propagates. It might lead to inundation. Or there might be a huge extraterrestrial object which is falling, which might lead to generation. Again, there will be disturbance, might propagate, and might inundation, might lead to inundate. So tsunamis are occurred, can be generated by various events like earthquakes, landslides, volcanic explosions, or meteor tsunamis. Meteor tsunamis are quite complex and they are very rare. In these meteor tsunamis, on the free surface, on the free surface of the ocean, when there is wind, the external pressure, they should meet certain criteria based on the frequency of it. Then these winds drive this free surface into disturbance, like generation, initial deformation like thing. They propagate towards the coast and might lead to inundation. These meteor tsunamis are complex. They are under research now. The reach of the meteor tsunamis is very less compared to the extent of land of inundation. In case of meteor tsunamis is less compared to earthquake inundation or landslide volcanic eruption. The devastation is less, I mean. So most of the tsunamis, 70 to 80% of the tsunamis occur because of earthquakes. So in inquest here, our interest is study the earthquakes, study the tsunamis generated by the earthquakes. So mostly we concentrate on the tsunamis generated by the earthquake. So the classical approach of tsunami is we have a free surface, a quite calm free surface ocean. Suddenly there is an earthquake at t is equal to 0 time. So earthquake has generated. This energy will be propagated to the free surface. It will undergo deformation. It will rise to some height, leading to tsunami, and under gravity, it will propagate towards the coast. After some time, there might be even second event of earthquake where a second cycle of tsunami wave might come down. After some time, there won't be any disturbance. After certain amount of time, then the sea might come down to the calm position after a couple of hours. So the point I would like to highlight here is tsunami involves 3 steps: generation, propagation, run-up, and inundation. Now, having said that a tsunami is a devastating event, tsunami has 3 steps, and the meteor tsunamis, there is yet another natural calamity called storm surge. In case of storm surge, the winds push the free surface towards the coast, where the free surface propagate and might lead to inundation. So in case of storm surge, storm plus surge, the sudden surge means sudden increase in the mean sea level because of storm is called as storm surge. Now, storm surge and tsunami both might lead to inundation. So here is a typical video how there will be inundation. So there is a propagation and the wave reach towards the coast. There will be a sudden rise in the sea level. All the water enter into the low-lying areas, inundating it. See here the free surface of the ocean have entered into the land and it has inundated the areas. Now the ocean water is passing from this route. It has entered into the roads and it has inundated the complete parts, inundating houses, the vehicles to certain height. So this we call as inundation. So all low-lying areas will get inundated. Now, the characteristics of tsunami. When having said that tsunami involves 3 steps: generation, propagation, and inundation, there are certain characteristic features of tsunami. So there would be a disturbance in the deep ocean at the seabed, which is an earthquake. Energy is transferred onto the free surface, and there will be a deformation. A tsunami is generated. Now, when a tsunami wave is generated in the deep ocean, the velocity, this tsunami wave propagates towards the coast under the gravity. When it is propagating, it will have a certain velocity, where the velocity is given by v is equal to square root of g into h. It has certain velocity. The tsunami wave travels with certain velocity, where the velocity is given by square root of gh. G is the acceleration to the gravity, 9.8, take it as 10 meters per second, and 10 meters per second square, and then h. H is the depth at the location. What is the depth at the location? So this gives us the velocity of the tsunami wave. Having said that, we quite know well that when we are moving from deep ocean to the coast, the depth of the ocean keeps decreasing. So we have a large depth at the bottom, and when you are moving towards the coast, depth reduces, and at the coast, at the shoreline, depth is 0. Now here, as the depth is high, as the velocity, the height, the velocity of the tsunami wave will be very high in the deep ocean. So here, where the depth is 5,500 meters, the wave speed of tsunami is 835 kilometers per hour. Whereas when it is moving towards the coast, as the depth decreases, the tsunami also reduces. When it comes to the coast, depth further reduces. Similarly, the speed of the tsunami reduces. The continuous cycles of tsunami waves comes. They move with a large speed. Speed reduces here. As a result, a lot of wave trains are piled up here. And here, the wave interacts with the bottom of the sea, where there would be a even friction. So a high-speed wave is moving fastly and suddenly enters into low region. It gets shooted up. So this phenomenon, which is quite complex and highly non-linear, we call it as shoaling effect. So because of shoaling effect, when tsunami enters into the coast, the wave height of the tsunami enters. The wave height of the tsunami increases or rises when it enters into the when it crosses the coast or enters onto the coast as depth decreases. Now here, the wavelength of the tsunami is very large in the deep ocean. Is very large. The wavelength would be of around half an hour to 30 minutes to 40 minutes. I mean, if there is a crest at present minute, after 40 minutes to 1 hour, there will be again a crest. I mean, it takes a long distance and long time to make one complete cycle. So as depth reduces, the wave height increases, it enters into the land and inundates. So this is the typical characteristics of the tsunami wave. And there are different terms to be known while we study or while study these characteristics of the tsunami. In the open ocean, we call it as the wave height. From the mean sea level, what is the height of the tsunami wave? That is what is our interest. We are interested in calculating the wave height eta. This is our interest of calculation. Here d is the depth. D plus eta added is called as wave elevation, is called as water elevation. Only height from the mean sea surface is we call it as wave elevation. And the wavelength is distance between two successive crests or troughs, or where the particles are at the same phase. So we are supposed to calculate eta whenever we solve the problem of tsunami. At a given depth, for a given location, for a given earthquake generation, what is my wave height? Is wave height going to be abnormal, very high, so that it might inundate the land, so that we are not safe, or my wave height is less, so that we are safe? So that is my interest. I am interested in calculating eta, the wave elevation. Now these are the plate tectonics. So for India, we have convergent convergent boundary tectonics and divergent boundary tectonics. Whenever we have a convergent boundary tectonics, we'll get the convergent boundary plate tectonics region. They are prone to earthquake. They might lead to earthquake. The contact areas are called as faults. They might lead to earthquakes like a strike slip fault, or a normal fault, or a reverse fault. These faults will give sufficient energy to the free surface. Say on the top of this, for example, we have ocean. Say because of this earthquake, energy will be propagated, and exactly top of it, the free surface will rise. Okay, a tsunami will be generated and it will move towards the coast, propagation and inundation. So these three earthquake fault mechanisms might lead to tsunami. Out of all these three, reverse fault is more dangerous. There are a lot of chances that this reverse fault might lead to a tsunami, which gives you more wave elevation. Now, whenever these fault earthquakes are possible, whenever we have a convergent boundaries. Whenever we have divergent boundaries, at the divergent boundaries, the plate tectonics, they move away. The under mantle, the liquid, the hard core will come out. There is a possibility of a volcanic eruption. There is a possibility of volcanic eruption whenever we have a divergent boundary. Because of this volcanic eruption also, there's a possibility of tsunami. So in case of India, we have convergent boundaries in the ocean at this region and at this region. So these two regions are the potential tsunami-genic zones for India, for east coast of India and west coast of India, complete Indian coast. This subduction zone, this tectonic plate where there is a possibility of earthquake, tsunami-genic earthquake, we call this as a Makran subduction zone. And this tsunami-genic earthquake, we call it as Sumatra subduction zone. So we completely tsunami-genic threat to India, Sumatra subduction zone and Makran subduction zone. Now imagine there is an earthquake either in the Sumatra subduction zone or Makran subduction zone. Whenever there is an earthquake in the Makran subduction zone, the nearest coast would be Gujarat. The time taken by the tsunami, which travels with high speed in the deep ocean, and it reduces its speed when it comes to the coast. Remember, velocity is directly proportional to square root of GH. It takes around 2 to 3 hours. Whenever there is an earthquake in the Makran subduction zone, tsunami wave will take around 2 to 3 hours to reach the coast, west coast. And if there is an earthquake in the Sumatra subduction zone, it takes around 2 to 3 hours to reach the east coast of India, and it takes around 20 minutes to 30 minutes, 20 minutes to half an hour to reach the Andaman coast. So if imagine there is an tsunami-genic event, and imagine there is a tsunami-genic event triggered, and we have captured, we have got the earthquake details. Now I have to simulate, I have to find out what is the wave height at the coast, at the east coast and at the west coast. So how much time I have? I have a time of 2 to 3 hours. So within this 2 to 3 hours, I have to analyze the earthquake. I have to see which earthquake it is. I have to generate the initial deformation. I have to solve the phenomenon. I have to calculate the wave height eta at different locations and give a warning that whether the earthquake is leading to tsunami or not. If it is leading to tsunami, what locations are getting what height, what areas are going to get inundated. So these are my interests. So already having said that every physical phenomenon is governed by differential equations, even tsunami is a physical phenomenon. It is governed by a set of differential equations. So being it a fluid, it is governed by the Navier-Stokes equations. We have 4 equations: the equation of continuity and the equations of motion, equation of motion along x, y, and z, and the equation of continuity. The equation of continuity will give us wave height. The equations of motion will give us the velocities u, v, and w. Now we try to simplify every physical phenomenon so that we can obtain the solution quick, and we can obtain the solution fast with less computational effort. So having said that tsunami is caused by earthquakes, say this is a seabed, there is an earthquake, this is the free surface on the top of it. In typically, the depths are going to be around 3 to 4 kilometers. Okay, in the deep ocean, say the depth is going to be around 3 to 5 kilometers approximately. And the wavelength of the tsunami is going to be hundreds of kilometers, right? The wavelength of the tsunami is going to be roughly around 100, 200 kilometers. The wavelength of the tsunami compared to its depth, the depth is 4 to 5 kilometers, and wavelength of the tsunami is hundreds of kilometers, right? So compared to wavelength, depth is almost negligible. 4 kilometers, 100 to 200 kilometers, quite negligible. So the wavelength lambda is very much greater than the depth h. So in this case, we can approximate these equations. We can neglect the component along the z-axis, right? We have 3 axes, x, y, and z. So the equation along z-axis, this equation can be neglected. So what we can do is we can integrate these equations. We can discretize the equations with respect to depth. We can integrate along the z-axis with respect to depth. Then we end up with these equations. We call them as shallow water equations. Okay, so Navier-Stokes equations with the shallow water approximation. Shallow water approximation is wavelength is very much greater than the depth. Depth can be neglected. So we can integrate the Navier-Stokes equations along depth, and we end up with the equation of continuity, equation of motion along the x-axis, and equation of motion along the y-axis. So thus a three-dimensional problem has been reduced into a two-dimensional problem along x and along y. So in case of tsunami, after applying the approximation and all physical laws and conservation of mass, conservation of energy equations, we end up with shallow water equations. Now, my intention, my aim is to solve these shallow water equations. Okay, so if I solve these shallow water equations, I can get this unknown wave height eta. Why I have to solve these shallow water equations? My aim is to calculate the unknown. What is the unknown here? Unknown is nothing but wave height. This wave height, to what height my tsunami wave is rising. To what height my tsunami wave is rising. My interest is to calculate the wave height. So calculating wave height is called as seeking the solution for the shallow water equations. Now I have to solve it, I have to get the solution for this. Now how I am going to get the solution? Three possibilities: analytical solution, experimental analysis, numerical methods. It is known that tsunami is a complex phenomenon, so analytical solution for these cases is ruled out. It is not possible to have a analytical solution for this case because the solutions are quite complex. So no analytical solution, and experiment is ruled out. It is ridiculous or meaningless or a joke to tell that I will conduct an experiment, okay, in the real time. So the only option is numerical methods. So we need to employ numerical methods to solve shallow water equations to get the wave height, to find out for a given tsunami-genic earthquake to what height, for a given location to what height the wave is rising and what areas are getting inundated. Now, what are the different numerical methods available? As said, different numerical methods available are finite difference method, finite element, finite volume, and mesh-free methods. Now, if I apply finite difference method, already we have codes or written codes or packages available. We can apply codes like commit, Tsunami, Comcat, or most. Method of splitting tsunami, Comcat, community coastal ocean tsunami modeling, Tsunami model, tsunami, some full form, Coronel Tohoku University of Modeling and Inundation, and commit. Okay, these are the codes available. Mostly they are open source. They are based on finite difference method. They are used to solve the, they are used to simulate or model tsunamis. And there are models available. Methods like finite element method can be applied. And for this, we have codes like ATSERC, CASTM, Abacus, ANSYS, and CONSOL. There are also models available which are based on finite volume methods. Packages like Anuga, Clopac, FVCOM, OpenFOAM, and Fluent can be applied. Mesh-free methods, they are quite complex. They are rarely used. But we have a code called SPH, Smooth Particle Hydrodynamics, which can be employed to study tsunami. Now, having said that, our interest is to calculate the wave height, and having said different numerical methods and packages available. Now, what are my requirements to model tsunami and inundation? What are the requirements? First, the basic requirement is I need to have a numerical coding or numerical code or numerical package which is able to solve shallow water equations. It should have the capability of calculating propagation and also the flooding, inundation, that is wetting and drain, and it should support parallel computing. It is said here that the time taken, hardly we have 2 to 3 minutes, 2 to 3 hours, right? So 2 to 3 hours. Here in case of Andaman Nicobar, hardly we have half hour. So within that time, we need to do all the analysis. So our computation should be very fast. So it should support parallel computing. The code, the numerical package should support parallel computing when you're using in the real time. Now, every numerical method has 3 steps: pre-processing, mathematical step, and post-processing. So in the pre-processing, what is my area of interest? What domain is covered? Am I going to solve for Atlantic Ocean or a Pacific Ocean or an Indian Ocean? With Indian Ocean, what coast? East coast or west coast or both? What is my deformation? We need to have mesh covering the area of interest, covering the region of interest, right? Once we have area of interest, once we have mesh, we need to have the seismic fault parameters. Tsunami is triggered by earthquake. Earthquake have seismic fault parameters. With this seismic fault parameters, we will develop the we will generate the deformation. To generate deformation, we apply models like Manson-Smiley or Okada model. And solving what numerical method I'm going to apply, finite difference or finite element or finite volume. Okay, for solving we need to have a high resolution water depth, that is bathymetry is needed for propagation. So we need bathymetry, we need ocean depth at different points, okay, for propagation. And if I'm solving inundation, I need topography. When water enters into the land, it's called inundation or flooding kind of thing happens. So what various buildings are available, what are those heights? We need the elevation, land elevation part. We call it as topography. And then once we have pre-processing and once we have done solving, we have the data in hand, post-processing, right? How you are going to write the data? You're going to write the data in ASCII file or you're going to write the data in the .cdf file. Once we have the data, how I'm going to check, how I'm going to analyze the data. So I'm going to have wave heights, I'm going to have the travel times, I'm going to have the area. So we need the plotting tools like GIS or Octave, Python, MATLAB, whatever, various GIS tools, etc. available. And it is good to have even observations to validate our model. Sometimes even it requires observations, right? So these are the basic requirements. It involves 3 steps: processing, solving, post-processing. So we need a good model which supports parallel computing. We need high resolution mesh with the good information of bathymetry and topography, and we need a post-processing tool for analyzing and plotting the results. So these are the basic should requirements for the modeling of tsunami. Now, first we said tsunami is of 3 parts: tsunami, generation, propagation, and inundation. When I speak of generation, this step, what different parameters are needed? So we have an earthquake at the bottom. Earthquake happens at a particular longitude, latitude, and depth. So this longitude, latitude, depth is known. The earthquake occurs with certain release of energy. We call it as moment magnitude of MW. Moment magnitude represented by MW. So when there is an earthquake, I'll be knowing these 4 values: location of the earthquake, that's epicenter, and moment magnitude. Now, knowing this moment magnitude at the fault, we should know these 3 angles: strike angle, dip angle, and rake angle. These 3 angles are important. Knowing these 3 angles, knowing this longitude, latitude, we can calculate slip, means to what height this deformation has happened, to what height the 2 blocks are moved. This is called as slip, measured in meters. And we need fault length, the length of the fault and the width of the fault. So when we know the moment magnitude, there are certain scaling laws, empirical formulas. Using those empirical laws, once MW is known, moment magnitude, we can calculate slip, fault length, and fault width. But this slip, dip, and rake are not known immediately. So to carry on the model, we'll be having the historical data. So see here, all the black dots, stars, they are the historical data. Data is available since 1881 or so. So for those data, all the seismic fault parameters are available. So in the real time, whenever we have longitude, latitude, focal depth, and moment magnitude from the historical database, we pick strike, dip, slip, these 3 parameters. Using the empirical formulas, we calculate slip, fault length, and width, and we generate the deformation. Okay, once deformation is generated, we need to go for propagation. So for propagation, there is a huge requirement of good bathymetry. So these are 2 different bathymetry charts, where this is GIPCO 30 arc seconds taken for Chidambaram and Nagapattinam region, where this is the data which INCOIS has. Here the resolution is 30 arc second. Here the resolution is around 100 to 200 meters. This is obtained by merging ALTM, CARTOSAT, and SRTM. If you do numerical simulation of tsunami on this GIPCO 30 arc second and on this, the results will be quite different. Okay, why here? Why? Because tsunami, in the calculation, the differential equation of tsunami, we have depth of the ocean, depth of the accurate representation of depth of the ocean is important. Here you can see, in this case, the fine details like river creeks all are visible, whereas in this case they are missing. So if you use this kind of bathymetry, there would be a mismatch with the real observations. Either we will overestimate or we will underestimate. this fine bathymetry topography will give us good results. So the same thing, this here you can see, this is a coarse topography, zip code 30 second. This is a fine topography mixed, which is combined from SRTM, Cartosat, ALTM, whose resolution is around 100 meters or 200 meters. This is around 30 arc-second. Here you can see creeks, fine creeks are also represented here. Okay, we can see the fine representation of fine creeks, whereas the same thing are not represented here. So if you use this kind of data for modeling tsunami, the results will be really beneficial. Results will be very good. Now, next, sometimes, most of the times we need even observations. So these are the various tide gauges, BPRs, and wave radar buoys observations available in the East Coast. So these are accessible in the near real time. So in the near real time, we can calculate we can get the data. What's the wave height is going to be, and we can compare with the models, or we can see the data. Again, these are the governing equations, shallow water equations. So these are different terms. Now, these are these shallow water equations. On the right side, I have 0. The highest order is the first order. So these are first order homogeneous nonlinear shallow water equations. I can further simplify these equations. These are the nonlinear terms. I can neglect these nonlinear terms. I can take only linear terms. See, these are the linear terms. I can consider only linear terms, and I can study tsunami. Okay. See, here all the nonlinear terms have been neglected, and we're considering only linear waves, linear terms. This will lead to a faster computation and a quick representation. We can linearize the equation and even solve them for quickness. Okay. Now, when we're looking at these equations, the unknowns we have here, the interest is to calculate wave height eta, calculate m and n. They are the discharge fluxes, nothing but velocity u and v components on the free surface. Also here we have n. N is the bottom friction. Okay, n is the bottom friction, which we need to provide, which varies depending on the area. Now these are the typical mesh of the free surface. These points are called as nodes. So these points are called as nodes. So at these nodes, I'm going to calculate the unknowns, that is u comma v. And at the middle, I'm going to calculate the wave height eta. Okay, this is a typical grid which is basically used for finite difference method. Now, in this grid, water enters along the x-axis. I will calculate the flux m. Water enters along the y-axis. I will calculate the flux n. So normal to it, normal to the x-axis, normal to the y-axis. I'll calculate the flux. That is, I'll calculate the velocities u, v. Once I know the velocities u, v, I calculate the wave height eta. Okay, at the different nodes. So for a given time step t is equal to 0, I have earthquake. Earthquake has lead to generation. I have the disturbance. Okay, so I know the height here. I know the height eta. Okay, t is equal to 0. With this height, I'll apply that height to these equations. Okay, and I will solve m and n. Okay, at t is equal to 0 with these heights. For the next time step, t is equal to 1. For the next time step, t is equal to 1. I'll calculate u and v. Once I know u and v, I'll substitute u and v in this equation. I'll calculate eta. Okay. So using this u and v for the next time step, I'll calculate the value eta. Now I know eta. Using this eta, I'll calculate u and v for the next time step. Using this u and v, I can calculate eta. Like this, I'll propagate towards. I'll propagate forward with respect to time. Okay. So this is a typical discretization of the equations. Simple. We know the basic Taylor's formula, where df by dx can be written as f of x plus h minus f of x by h, the first order differentiation formula. So here these differentials are replaced. Here these differentials are replaced with the Taylor formulas. Unknowns are kept on the left sides. Knowns are shifted to the right sides. Okay, knowns are shifted to the right side, and then we solve it. So finally, we end up with an equation of the form ax is equal to b, right? B is the known right side, A is the unknown. Apply Kramer's rule or Gauss elimination method, calculate the unknown A. So this is typical discretization. So the typical algorithm looks like this: generate the grid, have the fault parameters, length, depth, the latitude, longitude, epicenter, strips like rake, etc. Apply Manson and Smalley-Yokoda model, have the initial deformation. If t is equal to 0, you have the wave height. Okay. Now apply the boundary conditions. Solve u comma v. Using this u comma v, move to the next step. Calculate the height. With this height, calculate u comma v velocity for the next time step. Calculate the height again, and we'll move with respect to time. We march with respect to time. Okay, this is a typical algorithm. How algorithm works. So, as we need a faster and quicker calculations, we need to use GPUs or we need to use parallel computing. Okay. So an example how Tsunami is model, I show it on December 26, 2004 tsunami. You know very well about December 26, 2004 tsunami. It's highly devastated tsunami. It killed a lot many people, approximately around 2 lakhs plus number of people. A huge loss of property was there. So these are the initial fault parameters. Using these fault, this is the given. This is a GIPCO bathymetry we have used. The bathymetry at different locations. These are the fault parameters. Using this fault initial deformation. This is the initial deformation. See, the earthquake has triggered, raised the free surface to a height of 8 meters. Now, under gravity, this will move towards the coast. So this is a typical animation of the wave. How tsunami, December 26, 2004 tsunami have propagated, which is modeled using finite difference method. Okay. So with respect to time, the wave moved towards the coast. So it has taken around 2 hours to reach the east coast. Now, here are the observations where we have compared the model values with the observations. They are quite in good match. So this is the typical travel time plot, which says this is a typical travel time plot. Which says for a given location, say my location is here, which is light green in color. What time at what time tsunami wave reaches? So typical green color is around 40 to 450 minutes. So it takes these many minutes for the wave to reach here. So we call it as a travel time plot. This is called as a directivity plot. It gives at a given location to what height the water has reached. You can see the complete east coast is red in color. That says the wave height is greater than 2 meters. So east coast have experienced a height of greater than 2 meters for this tsunami. So how different, how energy has propagated, how wave heights are propagated at different locations. This plot gives us that. Now, whenever we speak of tsunami, our interest is to have the travel time plot, to have this direction plot. That's it. Now here, for this methodology, we have used finite difference method. There are a lot of drawbacks with finite difference method. It uses nested telescopic grids, and the coasts are not well matched. So there are a lot of problems. If you want to have inundation, we need to have fine small grids. You need to have a very high resolution grids. This takes high lot of time, and coding complexities will be there. So using structured grid, we have a lot of difficulties. So we go for unstructured grids. So this is a typical unstructured grid measured with triangles. Here, these unstructured grids are very easy and makes our life simple. We can have coarse grid wherever we don't want calculations. We can have a fine grid wherever we want good number of calculations. This also represents coast finely. So we prefer unstructured grids over structured grids. So this is a typical mesh of the Indian Ocean. Indian Ocean meshed with unstructured grid. This is a typical bathymetry. This is how unstructured grid looks. When we zoom it, at the required portion, we can have the required resolution. Here, the resolution is around 100 meters. In the deep ocean, the resolution is around 10 kilometers. We can mix up your bathymetry, ALTM, Cartosat in the required regions. We can mix up. We can combine the data. We can come out with a mesh. So there is a numerical code called advanced calculation model, which solves shallow water equations using finite element method on the unstructured mesh. It also solves the shallow water equations. So the IIRS also supports parallel computing. You can use as many number of processes you want. So it also supports parallel computing. It solves on the unstructured grid, which is highly beneficial. So this is a typical 26,004 tsunami initial deformation, which is solved on the unstructured grid. So the water has risen around 8 meters. Now, this is the propagation of tsunami at different time steps. You can see it has taken around roughly 2 hours to reach the east coast. Now, these are the wave heights of the numerical model compared with the observations. You can see RMSE and correlation at the top. There is a good match. So this is the travel time plot and a wave energy plot, which is the interesting thing. So this gives us a typical inundation. In December 26, 2004, Kadalur was the worst affected part. So here the water has crossed the coast, which is shown in black line. Water entered into the land, which is shown in blue color. This is all the inundated area. So lot of areas have been inundated. This is the zoomed part. So the unstructured grid could finely represent the inundation. You can see a fine inundation pattern here. The water has entered into these regions. So unstructured mesh is highly beneficial. They will give us the fine results. UTSRC is a parallelized code. It gives us results very quick. So this is a typical animation. This gives propagation, and these 4 plots shows the inundation. Okay, at different regions. This shows us inundation at Yanam, Pondicherry. This is at Kavali, Andhra. This is at Nagapattinam, Tamil Nadu. This is at Mahabalipuram, Chennai. Okay, you can see the water has crossed the land. So the area has been inundated. So the importance of unstructured grid is in the complete east coast, it is stretch in a single stretch, you can obtain the inundation, which is quite complex, quite impossible with the structured grids. So this is a typical propagation of December 26, 2004 in the complete world. Okay, so in the real time, the basic thing is acquisition. Means we need to have the seismic information, that latitude, longitude, magnitude, etc. With that seismic parameter acquisition, we'll do some processing. We'll calculate the initial deformation. We'll run the models. We'll analyze the results and see how the wave height is going to be and generate the bulletins. Right. So these are the typical seismic networks we have, which provide us with latitude, longitude, magnetic moment, etc. From this parameters, we generate initial deformation, and we calculate we call the model and we calculate the propagation and inundation. These are the various observations, tide gauges and the wave radar based observations, which INCOIS has in real time through satellite. They provide us data. So these are the various bulletins we represent. So if a wave height is greater than 2 meters, we say that area is under alert. If wave height is between 0.2 to 2 meters, we say that area is under watch. If wave height is less than that, that area is safe or threat has been passed. So depending on the wave height, we issue bulletins. So to summarize, we cannot have analytical. Every physical phenomenon is governed by differential equations or partial differential equations. We need to solve them using numerical methods. Various numerical methods are available. Tsunami is governed by shallow water equations. After shallow water approximations, we can apply methods like finite difference, finite element, finite volume, etc. We need to, our area of interest is to calculate the wave heights. We need to call the model. We need to launch the model. We have a very less time to respond in real case. So we need to issue the warnings as soon as possible. So a model should give us accurate results, and time taken should be very less. So we encourage parallel computing. Once we calculate the wave height, we use post-processing tools like GIS, Python, etc., MATLAB, Octave, etc. We plot and we issue bulletins. So our main interest is to calculate the wave heights. Yes. So that's all I have from my side.